So, yes, first off, thank you everyone for joining at the end of a long day. We appreciate you being here. I just wanted to start out by introducing myself and Jose and our company. So Jose and I are both with 4EA Building Science. We're a building enclosure consulting company. So in California speak, we are waterproofing consultants, and we also do some facade consulting. So basically all 6 sides of the building enclosure. So here we are. I'm Clarissa. I'm the Oakland office director, and we also have Jose on the phone.
I'm Jose. I'm also with 4EA building science specialist here. So I'm really excited to talk to you folks.
Yeah, and just a quick background about 4EA. It's a little tricky string of numbers and letters to remember, but a quick way to remember it is it's a play on words for the mathematician scientist Joseph Fourier, French guy. So it's a play on words. And we've got an office here in Oakland, and an office in Seattle, as well as one in Vancouver, Canada. So we offer kind of a full range of building enclosure services, including energy modeling, design reviews, building enclosure reviews, construction reviews, enclosure testing, all that good stuff. This is a background of some current projects that we're working on. We work on kind of all building types. Right now we're working on a lot of multifamily and affordable housing. So this is the Trans Bay 2 project. We're also working on a project called The Village in San Francisco, affordable housing on the top right there in El Cerrito. Homeless prenatal program is the middle picture there in San Francisco, and the bottom one there is a project in Alameda. And then some market rate multifamily here, one in Sacramento, one in Oakland here. It's already complete. So this is a mix of past and current, one in South San Francisco. And then beyond the multifamily, we also work on some commercial. We work sometimes on single family homes. So building size doesn't matter. We work from small to big. And then we also work on some existing buildings, re-roofing, building rehab kind of thing. We also work in Southern California. These are 2 current projects and one past project in Southern California. And then a shout out to our Seattle office. This is just a little selection of some of the Seattle projects. Again, similar, multiple different building types, new construction, existing. So that's a little bit about us, Fourier and me and Jose. And I am hoping to find out just a little bit about who we have on the line. So if you can use your chat box, if it's not showing up, you could click the 3 dots and find the chat box, and just let me know if everyone on the line is an architect, or do we have any contractors online, interior designers, any landscape architects. Yeah, we love to know who's out there, and just a little bit about that. So I see some good jokes of Archidork, and someone joining us from SoCal, and building enclosure consultant, and architects. And then I guess the follow-up question to that is, maybe the easiest way is yes, no, just are you familiar with building science and building enclosure? Majority of people are architects, so probably yes. But I'm just interested to know. Okay, it looks like we've got lots of good background here, so we'll try to keep it more advanced. All right, thanks everyone. Oh, I think when I was scrolling through the comments, I went to extra slides. Okay, so that's the intro. Now into the meat of it. As mentioned in the ad, this is an AIA accredited course, so you'll get one and a half learning units for participating, and the title is Towards a New Enclosure. This is our provider statement. It's pretty standard. Our learning objectives outline what we're going to be talking about today. Probably the easier way of outlining it is just the structure of our presentation. So Jose is going to start off by talking about the 2022 Energy Code updates, specifically related to the building enclosure. I'm going to jump in after that and talk about the building science behind those updates, explain that a little bit. And then we will jump into the weeds as we have it, which is basically showing examples of applying all of that stuff with different building enclosure details. And hopefully leave time at the end for discussion and questions. I will try to monitor the chat box as we go through. So if you have questions as we go through, we'll try to answer those too. We can do a little bit of both. To start out, we're missing our pop quiz, Jose. And you're on mute still.
My apologies.
But yeah, go ahead into the pop quiz.
Oh no, here, I'll give it back to you.
Okay. So just to start out, this is maybe a little trick to try to get everyone to pay extra close attention to the details. But a few questions that maybe you know already. And if not, we're gonna give the answers throughout the presentation. So first question is, for a 5-story multifamily building, in the previous code of the cycle, 2019, which part of the section would govern this type of building? Is it a commercial building? Is it a single family residential, or is it a multifamily residential? So that's question 1. Feel free, I guess, to record your answers for yourself. We're not taking them down. But as I say, once it comes to it in the presentation, we'll explain the answer. Question 2, can a building be too airtight? So possible answers: yes, the building needs to breathe. No, wrap that thing up tight. Or C, well, it's complicated. Question 3, water can move through the enclosure in a lot of different ways. Which of the below options carries more water? Is it uncontrolled vapor transfer? Is it uncontrolled air leakage? Or those two are about the same? So yeah, those are 3 questions to watch out for. And I will kick it over to Jose to start the code updates.
All right. Sorry for stealing the screen from you earlier. All right, can you see my screen now? And so like Clarissa said, we have the chat box here. So if you have any questions or anything, feel free to put them in there. And then we're hoping to maybe have a little discussion at the end of this and go through any questions. Or if we see anything pop up that maybe is pertinent to what we're talking about, we'll try and address those right off the bat. Here we go. So we are currently in the 2022 cycle of Title 24 generally, but we'll be talking about Part 6 here today. As we all know, that came into effect at the beginning of the year. And I just wanted to go through some of the building enclosure changes. But before that, I'd like to step back and kind of just put it all into perspective of kind of what we're trying to go for. So the state of California has some stated goals, and we can see here that the goal, which was very ambitious, was to have all new residential buildings be net zero energy by 2020. Obviously, we're sitting in 2023 and 2020 has come and gone, and there are various reasons why that wasn't quite achieved, but it was the stated goal. By 2025, the state is hoping to have all 50% of state buildings be renovated to be net zero energy. And then, of course, the big goal for a lot of organizations is 2030, where the state would like to have half of existing commercial buildings retrofitted to be net zero energy, and all new commercial buildings be built being net zero energy. And in this case, the definition of net zero energy is basically offsetting energy use that is offsetting the energy use that they do use with renewable energy over the course of a year. So just looking back at the last code, the thermal enclosure changes in 2019 were pretty minimal. 2022, so this new cycle has some more impactful changes to enclosure design. But basically the long and the short of it is there has been a change in classification of high-rise residential buildings, and also generally speaking, better windows and better steel stud walls kind of across the board. And there's also some new language for air barrier requirements in the code, which I am going to dig into a little bit more. In addition to that, for the enclosure, there are some other items that do impact the enclosure that did change. I won't go into them too much here, just in the interest of time, but reflectivity of steep slope roofs is one thing that's different. And there's also more stringent definitions for existing building renovations. So in 2019, the code kind of broke things up in a way that's always been a little interesting. So high-rise multifamily, so any buildings that are multifamily more than 4 stories were kind of lumped in with the non-residential, hotels, schools, commercial buildings into that section, with multifamily, so low-rise multifamily being in its own section, and then of course single-family homes. So a big change that happened this year is that the multifamily generally, so high-rise multifamily and low-rise multifamily were kind of lumped together. It is a big change in that if we look back at what the goals were, if you recall, the goals for residential buildings is more aggressive than commercial buildings. So there was a little bit of a jump in 2022 for some of the requirements, prescriptive requirements for high-rise buildings. We'll kind of go into that. And just to be clear too, what I'm referring to here are prescriptive requirements. So I understand, of course, not all projects comply with the code prescriptively. but it kind of all feeds through into projects. So if a building is complying with the energy code via an energy model, the reference building then adopts these prescriptive requirements. So that actually answers one of the questions in the pop quiz. So a 5-story multifamily building in the previous code cycle, 2019, it would be lumped in with what we would consider the commercial part of the code. So now it's in the multifamily part of the code. So jumping into some of the improvements, in the 2019 code cycle, all glazing was not tied to the climate zone. So it was glazing requirements were kind of standard across the board for building types, not impacted by the climate zone. So now they're spread out and they're climate zone dependent, just like walls. And in addition to doing that, these zones, so in blue here, fixed windows have a more aggressive, so they need to be more energy efficient target. And then similarly, the orange zones for curtain wall and storefront need to have more efficient windows as part of their prescriptive requirements. So what we can see here, just showing this in kind of different wording, 2016, 2019, these requirements were largely the same, and they were irrespective of the climate zone. But in 2022, these were split out across climate zone, so it's climate zone dependent, and also where it changed, they got more aggressive. Similarly for, and then similarly, the solar heat gain coefficients also drop respectively with U factors, so with the thermal performance of windows in these areas. When we look at high-rise residential, the drop is more significant in that by changing the type, basically we moved, we have some pretty aggressive drops. So we can see here up to, let's see, so from a 0.45 down to 0.3, or from a 0.41 to a point, sorry, I'm losing myself here, to a 0.25. The drop is really aggressive. So it's maybe more than 30% in some instances. Certainly not anything that the market can't bear, but something to be cognizant of when specifying fenestration products in multifamily. And then similarly for opaque walls across the state, across all climate zones, have higher efficiency targets. These are for metal frame walls. And in the blue, there's about an 11% reduction in the thermal conductivity. So it needs to be about 11% better. And then in the green, about 13% better. So similarly, we can see that here in 2016 and 2019, there was no change in the non-residential steel stud kind of baseline requirement, but then there's about a 11 to 13% drop in allowable conductivity in these walls, so they need to be about that much better for 2022. And then of course, looking at high-rise residential, the drop is still it's more aggressive depending on your climate zone, because steel stud walls generally have been climate zone specific. And then we can see here, weirdly in zone 15, actually, walls are allowed to be just a little bit worse. And that's just a kind of a side, just downstream impact of that change. So what does that mean for us here in the Bay Area? Basically, in 2019, where we could use an R25 steel stud wall with a couple inches of mineral wool insulation on the outside, now we basically need to add an inch of insulation. So we can see here from an R6 to about an R10 to comply prescriptively with these baseline requirements. So those are the requirements kind of from a U factor thermal performance. The other big change that we see in the code in this cycle are air barrier requirements. The wording of air barrier requirements has changed quite a bit. Now, so there has always been a requirement, kind of a qualitative requirement for air barriers. Well, they're not always, but there has been for some time a qualitative requirement for air barriers in the code. But until recently, only climate zones 11 through 16 had additional requirements for air barriers. Now those are across the full state. And I don't intend to have everyone squint and read this, but this is the wording from the code. And I was hoping to kind of walk through it a little bit here. So there are 3 parts, A, B, and C. And if we look at A, this is the first change that has kind of a notable change to our practice. So what this says is that construction document, so there are jurisdictional requirements now for how to document the existence of an air barrier. So it says that air barrier shall include air barrier boundaries. There will be details that show the connections of interfaces. And also we need to start showing square footage calculations to say kind of what the size of the air barrier document is. So this is a new requirement for California. Up in Washington State, our Seattle office has been exposed to a similar requirement since about 2019. So we've had a lot of opportunity to kind of see how this looks. Basically, it just means drawing a line around what we would call the thermal boundary for the building. So wherever we want the air to stay an inside temperature, that's where the air barrier tends to be. So for a building like this, it kind of very clearly follows just the exterior of the building. But when we get down into the lower levels where there are back of house spaces, maybe there's garages and and vented mechanical spaces, that air barrier boundary kind of meanders through the building. So that all needs to be defined on drawings. And then also there needs to be basically an air barrier takeoff, showing the square footage of all 6 sides of the building. So the walls, roof, bottom. The second part of this requirement, B, is wording that we're all probably already familiar with. It was already in the code in kind of in a different way, but or in a different kind of presented in a different way. But basically what this says is to have an air barrier, you either need to use air barrier materials. So those are materials that in this case do not exceed a permeance of 0.004 cubic feet per minute per square foot of enclosure area. Or you can use airtight assemblies. So when we go from materials to assemblies, we allow for an order of magnitude kind of reduction in performance. So that's just kind of the engineering mindset behind the numbers here. So you can use assemblies that demonstrate performance of not exceeding 0.04 cubic feet per minute per square foot of enclosure area. So you can do one or the other, and you can comply with section B in that way. The section C is the one that can be a bit of a head scratcher because it says that there's now a verification component. This is what's new for California, and but the wording says that verification of the installed air barrier may be performed. So may is the operative word here. My understanding, just based on kind of reading the reasoning behind kind of how the code was developed, is that the state wanted to introduce this wording so that air barrier can start becoming a better part of the lexicon for the industry. But they were concerned with mandating that verification must occur in this iteration, just based on the based on the difficulties in qualifying, for example, who would do these activities. But with that said, what this requirement basically says is that Another way that the air barrier may comply with this section is that the whole building would need to be tested, and the whole building would need to be demonstrate air tightness at 0.40 CFM per square foot of enclosure area. So if you recall, with the materials, we have 0.04, 0.004 units. With the assemblies, we allow an order of magnitude drop in performance. And then if you step up to the building, we allow another order of magnitude drop in performance. So that's kind of where that 0.40 number comes from. Section B here says basically the same thing, but if a building is very large, you can test it in segments. And then item 2 here actually puts a ceiling on performance. So it says, basically, if you test the building and you don't meet that 0.4 CFM per square foot requirement, do these things, right? So you can do a visual inspection, do some diagnostics, write a report, and then you comply. So there's a path to compliance even if you don't meet that requirement. But it does place a ceiling. So it says, but if the building is above a 0.6 CFM, then you basically need to make it comply. So you need to make changes, retest it so that it is below that 0.6. So what I see here is that this is a requirement that you don't necessarily have to do, that has a that has a stick. Okay, there's a carrot and a stick. So for that reason, our impression is that the industry probably won't start doing this voluntarily, but the signal we're getting is that this is being placed so that maybe in another iteration, the requirement would become a mandate. Our Seattle office has seen this requirement in Washington State since 2009. So there's been a good history there of testing and kind of watching how the industry responds to this type of requirement. So I think it's interesting here to kind of look at what happened in Washington State and just to get an idea of what could happen in the California market. So the way that section C, generally works in practice is basically you have a building, the building's air barrier has been designed in documents, the outline is drawn out and defined, the area is known, and then the building gets built. And then once the air barrier of the building is installed, usually that happens near the end of construction. Someone comes in with a bunch of large blower door fans and starts to basically inflate and then deflate the building. The theory behind it is each of these fans is calibrated. So we can measure the amount of air flowing through each fan at some reference pressure. And then we can use that to know how much air is thus leaking out of the enclosure in an uncontrolled way. This type of testing is typically done it's much more common on single family homes in much of the country, but it can be done on very large buildings as well. And then of course, when you're doing it, there's always an opportunity for diagnostics, in this case through infrared, but there's also smoke pencils and all that to kind of try and find where air leaks might be occurring. So in 2009, this requirement was introduced into the state of Washington, and the state of Washington said, kind of similar to California, the target is going to be 0.4 CFM cubic feet per minute of air leakage per square foot of enclosure area. And then the code was ambiguous. It didn't tell you what happens if you don't meet the target. So our team up there started doing a lot of testing, and we've collected some data. And what we have here is a histogram. So it's a relative frequency graph. And of course, the way you read it would be each of these shows the relative frequency of these results. So results on the bottom, percentage of buildings tested on the y-axis here. So what we can see is that the buildings that demonstrated 0.2 that were tested under the 2009 code, about 22% of the buildings complied at 0.2. about 22 complied at 0.15 and so on. So we can see here, if we place a line at 0.4, which is the target, most of the buildings in 2009 complied. Some of them didn't, but many of them did. So then there was a code change in 2012. The state said the target is still 0.4, and if you don't comply, kind of like similar to what California has, do these things. Take some infrared scans, some smoke pencil scans, and whatnot, write a report, and then you comply. But what we can see is that the market kind of responded. So in 2012, after a code cycle, we can see a tightening of the results of the buildings that we tested, where many more of them complied with that 0.4 requirement, which I've highlighted right here. In 2015, there was another change in the code, and in Washington State, and what we can see is that the building tightness that was demonstrated for buildings that were tested under that code cycle actually got even tighter. So what this shows us here, when we kind of put them together, is that two things. So there is definitely a there's definitely a learning curve when it comes to demonstrating and building for air tightness in a market. So it's not easy, it takes effort, but it's certainly doable. It just takes time for markets to respond. So right now in 2021, which is the latest Washington State code cycle, the new target's going to be a 0.25, but we don't have good data on 2018 or 2021 yet, because those are all still being built and tested right now. So that is kind of the long and the short of the code, and I'll hand it back to Clarissa to go over some building science. And you're muted. Oh, there you go.
Okay, yeah, so the point of this section is kind of to give the theoretical background, some of the science behind those building enclosure changes. I subscribe to the theory that in order to do things, you should understand the theory behind it. So that's kind of our objective here. And then after that, so this is kind of the backstory. And then once I'm done with the backstory, part 3 will be the advanced story, which is how to put this into practice in building enclosure details. So building science is kind of the theoretical basis for all of this. And I like to explain it as the control of energy moving through the building enclosure, so the outside of the building. You can control a whole bunch of things moving through the building enclosure, like noise for acoustics. You could air in terms of air quality, daylight. Today and generally in our practice, we focus just on these top 4. So liquid water, air, heat, and water vapor. So we're going to focus mostly on those. So begin with liquid water. We've really been enjoying a lot of defense from liquid water in the last months and over the winter here with intense rains that we've had. With the drought previously, maybe it's been a bit less of a focus, but controlling liquid water really is one of the main concerns in the Bay Area, and has been a focus. But with changes in the building code, we are moving a little bit more towards heat and air being more important. But in terms of liquid water control, the main way of managing it are the 3 Ds of water control. So deflection, drainage, drying, and durable materials. So An easy way to think about it is basically the rain screen and how a typical rain screen works. So the exterior cladding acts as the deflection layer, deflecting 90 to 95% of the rain. Then we have a gap behind that cladding that provides drainage, and with given some ventilation, some drying. And then behind that is our weather barrier, and that's the durable material. So it's protected from the outside, increasing durability, and it's continuous, also providing a weather barrier that hopefully lasts for a while and keeps the water out. So yeah, the liquid water management is not necessarily anything revolutionary, but very important for our buildings in the Bay Area and California. Moving on to heat and thermal control. Here we have kind of one of our standard images of an infrared scan of a building, showing areas of the building where there's more heat being lost, and areas of the building where there's better insulation. So when we're talking about heat loss or insulating, the starting point is really remembering high school science and the 3 modes of heat transfer: conduction, radiation. So convection would be the movement of heat through the active movement of particles through liquid water, or through liquids or gases. Conduction would be the movement of heat through the particles in solid matter, and then radiation being the electromagnetic transfer of radiation, for lack of a better word, in all 3 of those states. So solid, liquid, gas. And the reason why I'm pointing this out is that our insulative materials are all designed to optimize for this, and to try to decrease heat transfer by controlling these modes. So insulation, for example, is at a set density so that so that air doesn't create little convection loops, but it's not too dense so that it's not too conductive. And then in some cases it might have a reflective covering to reduce radiation. Similarly, our insulated glazing units are designed with a specific gap width to try to reduce, the opposing forces between convection and conduction. And we have the coating for radiation. So those are kind of the reasons why we want to understand the different modes of heat transfer. Beyond those modes, have a little bit of explanation about units. We come across these a lot when looking at insulation and specifying thicknesses and looking in the energy code. So it's helpful to understand what the units mean. So for conductivity, i.e. heat flow through a material, it's basically looking at the energy flow for a certain unit of wall area. So that's the heat area, or sorry, through wall area, that's heat squared. And then for a certain temperature difference, so that's the degrees Fahrenheit over a certain time period. So those are the metric or the units that we use here. And then if you're going over to scientific SI units, it's watts per meter squared Kelvin per second. So it looks like you've lost the time component when you go over to watts per meter squared Kelvin, but watts actually break down into joules per second. And so those 2 units are just basically a conversion factor between the 2 and are equivalent units. So that's conductivity. And then R value is the inverse of conductivity, which is the resistance, resistance to heat flow. So you can see those same units are just flipped upside down. So BTUs are on the bottom and feet square Fahrenheit hours are on the top. And same thing with the RSI units. The reason why this inverse relationship is important is essentially that for every U value that you add, the first bit of the thickness of your insulation is the most important. It provides the most resistance to heat flow. And then for every bit you add after that, you get a smaller and smaller incremental gain in terms of the ability for insulation to resist. So the presence of insulation is super important in keeping your building insulated, but continuity is also a really important factor. Essentially, heat will find the path of least resistance and flow through it. And we have this slide because the flow of water is a really good way to visualize that. We don't get to see how heat moves and flows, but water does the same thing. It finds the path of least resistance and it flows through it. So in this case, there's spots where the water is getting through the dam, and those are the areas of weakness. So in the same way, thermal bridges through the enclosure are going to be the weakest areas and conduct the most heat. All right, moving on to air. So our air is all around us. We don't necessarily think about it all the time when we're thinking about the air, about the building enclosure. But it is a really important component to control in terms of interior comfort and durability. A whole bunch of things get carried by air and air movement. So an example of that is sound gets carried through. So an airtight building enclosure actually provides a quieter building. Pollutants, bulk water also gets carried, and temperature. So there's a whole slew of things that we want to control and can be controlled through airtightness. One area of distinguishment is air leakage is not the same, or air leakage is uncontrolled and unknown, and air leakage is not the same as ventilation. So if we get the building to be entirely airtight, then we can control our ventilation and basically allow the building to breathe. There used to be a fear that if our building is too airtight, it won't be allowed to breathe. But in reality, if it's airtight, we can actually control our ventilation better and also recover heat if necessary. So that's one of the answers to the question that we had at the beginning. Can a building be too airtight? And the answer is no. If you wrap it up tightly, you can then ventilate for fresh air. And in fact, a lot of times you can size mechanical systems to be smaller if it's quite airtight, because the ventilation can be quite efficient in terms of motors and fans and such. And then this slide is just a photo from San Francisco from I guess it would be 2 or 3 years ago now, from fire season, and the air pollutants and air tightness was important because it was much more comfortable to be in a building with good ability to filter out air. All right, moving on to gaseous water or water vapor. Um, we've we split this up from the first topic, which was liquid water, and this last topic, which is gaseous water, because they act quite differently, and they're both important in terms of the building enclosure and control layers. So we use quite frequently this psychrometric chart to understand um, how water vapor is acting and reacting in the environment and how it needs to be controlled. So in this example, we have uh, kind of room temperature air. So along the horizontal axis, we have the temperature, and then these curved lines represent the relative humidity, and the vertical axis represents how much water is in the air. So if we have kind of a standard room temperature around 72 degrees Fahrenheit, 40% relative humidity, which is kind of a standard relative humidity to exist at. We want to know at what point will water condense out of this air if it's cooled and if there's any danger of condensation. So if we're looking at that air and we cool it down, which is basically sending this air over to the left to the 100% relative humidity line, at what point does it condense? So once it reaches this 100% line, that's the point of condensation. And that's at about 47 degrees Fahrenheit. The reason why this is important is then we want to make sure that surfaces that can be reached by this air are warmer than 47. Otherwise, we will be reaching a situation of condensation. So depending on the air temperature outside, depending on your glazing, like a single glazed building, it might actually be easy to get down to surface temperature. All that being said, vapor is important. It can cause troubles within a wall assembly if it's not managed properly. But air leakage or uncontrolled air leakage can transport a lot more water than vapor drive. So in this situation, if there's an opening in a wall with uncontrolled air leakage, it can carry bulk water through and carry quite a bit more water than vapor diffusion, depending on pressure differences. So that brings us to the answer to quiz question number 3, which was which mode carries more water through the building enclosure? And so uncontrolled air leakage can carry more water and carry water faster through the building enclosure usually than uncontrolled vapor transfer. So that's kind of the backstory on all of those main 4 components that we're trying to control with the building enclosure. And so when we're looking at those 4 components in the real world in designing for buildings, we will look at these details and put our building science glasses on and start drawing lines. So on the right-hand side here, we have a fairly standard wall assembly. So this would be a framed wall with that insulation, some exterior insulation, and then a weather-resistant barrier. So we draw on our water control line, we have our air barrier, we have thermal, and then on the flip side, we have kind of a standard cast in place wall with similar lines just in different places. Taking that, we can flip it around the side and make that into a roof assembly. And we have similar lines. So the vapor barrier below also forms the air barrier. And then we have the roofing that forms the water and thermal. And then take that, flip it around again, and you can get either the floor assembly, or in this case, this is reflecting more of a soffit condition. Same thing, got a thermal line, water, air, vapor. The tricky part comes in then when we start trying to join the walls with the roofs, with the soffits. And at these interface details, we can come across some tricky situations. So as you can see in the upper right hand corner here, the control layers are kind of crossing all over the place. This can lead to some issues in construction, and of course it's doable, but you have to come up with some more nimble solutions, and maybe it's more labor on site than it needs to be. Whereas this lower left-hand corner, the lines are straighter, one thing is attaching to the other, and the material interfaces are going to be a lot easier. So I'm going to take us through some detail examples, and essentially we're aiming to be lower left-hand corner people and not upper right-hand corner people. Okay, so this is our part 3 of the presentation, into the weeds. All right, so this first example is basically a curtain wall sitting on top of a cast in place wall. And so we've got some exterior insulation, some cladding. And so if we start drawing on our usual lines, we can see a few issues here with and I should say the curtain wall sitting out on this shelf angle. Firstly, thermal. There's no continuity between this exterior insulation and the insulated glazing unit out here. So this shelf angle is creating a thermal bridge. There's also the air water vapor barrier is not continuous or jumping across this shelf angle either. So the air weather barrier is here behind the thermal insulation. The shelf angle is interrupting it. And then the air seal that would happen at the back of that insulated glazing unit doesn't really translate down through the shelf angle. So what can be done about this? The answer, there's not one answer for anything, but if we don't catch this until late in the design process or into construction, the solution that you can do is maybe limited and not the highest performance. But this would be one approach if you can't make major design changes. So the approach would be to send some insulation out and try to cut off that thermal bridge by adding insulation here. You can see there's still a break in it. So again, not the perfect solution. And then again, adding a membrane in and sending it around this shelf angle to try to tie in with the glazing there. So a little bit of extra working and not the most elegant approach, perhaps. But ideally, this is something that you would catch earlier in the design process. And so this slide represents a slightly better solution, or a much better solution to this, which would be to bring the window in and bring the glazing unit in line with the exterior insulation So you can see that thermal boundary is pretty well straight up and down. And it also makes it a lot more straightforward in terms of the air water vapor boundary. You don't have to loop membranes around, which can be pretty tricky to do during construction. So by virtue of just moving that in, it wouldn't be a higher cost solution, and you get a much better performance. I have three other examples, so on to the next one. All right. This one again is kind of a standard situation. Down here we have a roof deck, and then we have a stem wall or concrete curb, and then a framed wall that's sitting on top of the concrete curb. So drawing on our lines, we can see we definitely have a disconnect in the thermal. So the red line is inside this concrete curb, and then there's a big gap and it jumps to the outside. And then similarly with the framed wall, it jumps around a bit there as well. With the weather barrier, it is continuous. It's just kind of zigzagging in and out, and that zigzagging maybe just means that there's more labor on site, more sealants being used, more tricky stuff. And then the air barrier, also not too bad. It can drop into the cast in place concrete. So thermal is probably the bigger issue here, but we can also somewhat improve the weather barrier. So this is one way of revising the wall to improve those lines and get us away from that complicated interface right upper right hand corner and down to the more straightforward. So in this case, we're bringing that insulation that was inside the cast in place concrete wall, and we're putting it on the outside. So and then we can provide a cladding. In this case, we've shown cast in place concrete because that will provide the same appearance as before, but this could be clad with something else, metal flashing or siding or whatever you choose. But as you can see now, our red line is continuous. And not only that, the weather barrier is more in the same plane, which makes it a little more straightforward for construction. And we are now in the better corner, the lower left corner of continuous control layers. All right, moving on to this example. This is from a mass timber building. So here we have a bump out. Basically, it's kind of an architectural feature of the building, where there's a bump out around this floor slab, which is a CLT floor slab. And in the process of doing a bump out, we have more space and we're thickening up the insulation. And probably the instinct is to say, great, we have more insulation, our building is going to be warmer. But in some cases, adding insulation can be a concern if the rest of our air barrier and vapor barrier are not in the right spot. So here you can see, they say, the double thickening up of insulation here. And we have our air and water barrier just running around the outside of the building directly behind the exterior insulation. So the concern here is basically that with the air and water barrier being out here, interior air that is maybe warm and somewhat moist can move through the insulation, which is warm also on the inside, but the farther that it moves into the insulation could get colder. Like that example that we saw earlier with the psychometric chart, and it could get to a point of condensation. So in order to address this problem, we want to switch up where the air barrier is, and move the air barrier farther to the inside, so that in this area where the insulation is being thickened up, the air barrier is on the inside and helping control that the interior air isn't able to move into this colder cavity. So boom, that cool blue moving dot gets stopped before it can get to the colder temperature insulation and condense. Oh, we managed to go through this really fast. It's only 7, but this is the final example for detailing changes and updates. So this is a pretty common condition that we see on more tower type projects that are clad with curtain wall. And so when the curtain wall gets up to the roof deck, the appearance that is desired is that the curtain walls continues all the way past. But there needs to be some building enclosure changes and building enclosure sealing off at that point. So here we are in section up at the roof deck. And in this detail, you can see that the curtain wall basically comes up to this kind of low parapet wall, and then the next unit stacks on top and continues up. When we look at our different control layers, you can see the water barrier is a particular issue. Because essentially the backside of the curtain wall isn't meant to control exterior water. And so we have this gap in the water barrier here. And then thermal continuity is somewhat of an issue as well, especially it's not necessarily shown well in this section, but at the vertical mullions, there's discontinuity in the thermal boundary there as well. So, and with this empty, unventilated space, there can also be some issues. So the suggestion to address all of those concerns is basically I'll start with the water part first. Lift up that curtain wall extension and add in a weather barrier to close off the top cap of that curtain wall, and make that water barrier continuous. And then from a thermal perspective, we're adding in some insulation on the top here. So you can see in this previous example, there's this void space, and there's also no insulation on this cap. And then we've added insulation on this cap, and that closes off the thermal barrier there. Oh, that is it for our examples and our presentation. You managed to motor through it a little faster than I expected, and I've been looking into the chat, but I don't see any questions. We're happy to answer any questions. I don't know if everyone is able to unmute themselves, but if you have questions, feel free to unmute. And if not, you can certainly use the chat to type them in. And Jose, I don't know if you have anything to add or
Yeah, no, I was going to say, yeah, we got through it in an hour, which is, well, I'm sure everyone, there's no need to keep people longer than they want to be, but we're happy to hang out and answer any questions. We're hoping for, discussion, and we can dive into details more if there's anything anyone wants to talk about. So we appreciate everyone hanging out with us tonight. Yeah, and I think, so I'm pretty sure people can unmute them. I don't know if there's silence because there are no questions, or silence because everyone's good. So
I think it's because it was explained just so well. Or the energy code put everyone to sleep. One or the other.
Fair enough.
So this is Don. I have a question.
Yeah.
Yeah.
How does ventilation affect everything that you just described? With the, there's got to be a supply and an exhaust to maintain the pressure within the building. So what does that look like?
Do you mean the mechanical ventilation, Don? Like the
Yeah, we need to breathe air. So how do we get fresh air in? And
Yeah, absolutely. So sorry, Clarissa, do you mind if I jump in on that one?
Yeah, go for it.
Yeah, okay. So typically what we would typically expect with the more airtight enclosure, you're right. Air needs to be then mechanically brought into the building. What we typically see is basically ERVs and HRVs to bring in that fresh air mechanically, and it becomes a balanced system. But with recovery being kind of the key driver to help kind of push down the energy consumption for the space conditioning.
and also for restrooms, the exhaust fans for toilet rooms and shower rooms.
Right, exactly. And for kitchens, so I think for kitchens and bathrooms, and this is where I'm getting on the periphery of where we typically dabble, just because that's we typically will work with someone kind of more on the MEP side for that. But I believe our experiences, those would then require some sort of makeup, just so that you don't have a negative pressure on your building.
Okay, and then I don't want to hog all the questions. I have another question.
No problem.
Once the building's all sealed up and pressurized almost, has anybody studied the effects of weather, like extreme weather events like tornadoes, hurricanes, or pressure fronts, and how the building's going to collapse during those events, just because it's under pressure?
Yeah, that's a good question, actually. I don't know that that's been studied too much. The air tightness for the build, so the pressures that the building is kind of designed for, so the reference pressure being around 75 pascals is much lower than you would get in a hurricane or like an extreme weather event. So at the risk of speaking out of turn, I don't think that would necessarily be impacted by the air tightness of the enclosure itself, but I mean, it is a good question.
I don't think people have studied it that much.
We were always taught, I'm from Kansas, so we were always taught that when a tornado is coming, open all the windows.
Just so that it can flow through the building.
Yes.
Yeah, that makes sense.
Okay, well, thanks.
Of course. So this is a joke, I guess, but sometimes when the tornado comes, the windows open themselves too.
Appreciate your time, and hopefully see you at the next AIA East Bay.
Thank you.
Thank you.